Tēnā koutou katoa and hello everybody. Welcome to the Lentil Intervention Podcast. My name is Ben Adelberg and I'm coming to you from Tamaki Makaurau, Auckland. Tēnei ka mihi ke te mana whenua o Aotearoa. And we acknowledge the local tribal authorities of New Zealand.
And g'day, I'm Emma Strutt and I'm currently coming to you from Durrumbul country in Queensland. Before we dive into our conversation today, I'd like to acknowledge the traditional custodians of country throughout Australia and their connections to land, sea and community.
We have a cracker of an episode ahead with another returning popular guest, and for me personally quite timely. As side note, I've just started reading Greta Thunberg's The Climate book, and already within chapter 3, they're short chapters, a contributor talks about civilization and extinction, which also has some very specific reference to New Zealand. So Emma, we return to an important conversation on biodiversity, and of course, who better than Corey?
Of course. So today we're very lucky to be chatting with Professor Corey Bradshaw, who's joined us previously in Season 2, Episode 10. So please check that out if you haven't already, because it was an incredibly important conversation. But for those of you who are newer around here, Corey is the Matthew Flinders Professor of Global Ecology and Director of the Global Ecology Laboratory at Flinders University. Professor Bradshaw has hundreds of peer-reviewed articles to his name, 13 book chapters and 3 books. Very busy man. Today we're going to mainly be chatting about one recent paper in particular, but I'm not going to give it all away in the intro. So we'll bring you on, Corey. Thank you so much for joining us.
Thank you very much. And I just want to say to Manina Pudni Nadlu Tapiti Alaka Nadlu Karna Yataka Imparenti. That's Ghana. So I'm coming to you from Ghana country in the Adelaide Hills. Actually, I'm on the border between Paramank and Ghana country. A little bit uncertain where the borders are really, but that was essentially saying that I acknowledge the Ghana people that on whose land I am today. And thank you.
Brilliant. Good. And not forgetting also you were a contributor to a season wrap-up that we did. I can't even remember which season it was. Season 2, I think, where we spoke about personal climate stories and impacts. And you had a wonderful story about, how you also see that impacting your daughter. So certainly to our listeners, let's go back to that episode as well. All of our episodes, if you haven't heard them or want to listen to them again. Corey, you got an intro from Emma, but just to our listeners, very briefly, what do you do?
Well, these days, I guess I'm mostly a mathematician. I don't say that in front of mathematicians, of course, but I do a lot of maths and a lot of coding. And what we try to do is put together virtual worlds to investigate plausible alternate futures under different scenarios of intervention. That's just a fancy way of saying creating a model that allows us to see into the future and look at what the relative effects of making certain decisions might be on society and life and the biosphere in general.
Okay. So Emma alluded to the fact we're going to explore a paper that you recently published in, I think it was December last year. But before we get there, let's talk about set some foundations here in terms of terminology, concepts, and so on. So biodiversity. Let's start off super basic. What does biodiversity actually mean, and why is it so important to the health of the planet?
Okay, that's quite something to unpack. Actually, the word comes from biological diversity, so it's kind of a shortening. I can't remember when it was first used, but it's been around the traps for a while. And you think about it quite superficially. You think, oh, it's just the number of species on the planet, but that's only one measure of diversity. So diversity could be genetic diversity. It could be simple, just number of species, but even that, we get a lot of hybridization. For example, in Australia, there's anywhere between 400 and 900 species of eucalypts because it's basically just one giant genetic gradient because they interbreed. It could be phylogenetic diversity, which is the evolutionary history, how long something's been around on the planet. Some species have been around more or less for hundreds of millions of years. Others have only been around for a couple 10,000. And the uniqueness therein. It could be how quickly that diversity changes over space and time. We call that beta diversity. So that's like a gradient of diversity. So it really depends on what you measure. Now, Why is it important? Well, this entire planet feeds off of itself. Now, that's a very blunt way of describing it, but essentially, all the species that exist because other species before them and that are around them today exist. So they create niches that can be exploited through evolutionary processes, basically to feed, reproduce, die, and then continue the life cycle. Without all of those species creating elements of another species' niche, the things that they need to survive, they wouldn't be around. A great example is pollinators and plants, flowering plants. 90% of flowering plants require an animal pollinator to reproduce, to complete their life cycle. Without those pollinators, they wouldn't be able to reproduce. Then they would die, obviously. Parasites and hosts. Parasites need hosts to complete their life cycles. If they don't have the hosts, the parasites die. Predators need prey. If they have no prey to eat, they have no food, they die. It's really that kind of simplistic. I mean, there's many subtleties and feedbacks and nonlinear relationships between all these species. But essentially, we know that the more diversity there is, no matter how you measure it, generally speaking, the more resilient a system or a community of interacting species is to an outside disturbance. That could be anything from like a bushfire or a cyclone or cutting down a forest or whatever that we constitute as some sort of force that causes death. If there's lots of species, then chances are you're going to be less likely to to be susceptible to that particular disturbance. Or if you even go outside of the species concept and you look more at the community of species, all these species perform different, what we call ecological functions. Some process atmospheric gases. Some, like plants, turn carbon dioxide into oxygen, right? We turn oxygen into carbon dioxide, animal respiration. So the combined effect of all these ecological functions, they have some redundancy in the system. Just like engineers will put in, say, triple redundancy when they build a bridge, right? Just in case a shock comes along, the bridge doesn't fall down at the first sign of a problem. There is ecological redundancy in a system. So if you lose one or two species, there's probably a few more that do more or less the same function and keep things ticking over. But at some point, and this is what is commonly misunderstood, is that you can get a lot of resilience and a lot of redundancy in the system, and you can have loss and loss and loss, and things don't really look like they're changing that much. And all of a sudden, some key species that no longer has any redundancy is lost, and the whole thing crumples into a heap. So it's not this gradual process. It tends to be very unnoticeable, followed by a catastrophe. And that's, I guess, the situation we're heading into now, is that in many systems are at that sort of collapse stage because they've lost most of their ecological redundancy. That was a long-winded answer. What is biodiversity?
It was a good one, though. It's important to understand these features. And like, as you said, like, say one animal goes extinct. It's very heartbreaking, but it's not in a silo. There's going to be flow-on effects. And that kind of brings us to a talking point that you mentioned in your paper that we'll get into in a minute. But the concept of co-extinctions and trophic cascades. What does the listener need to know about that interconnectedness? And do you think that the scientific literature to date has actually adequately addressed these concepts when assessing biodiversity?
Yes and no. Everything I say is guarded and conditional, of course, because I'm a scientist. I'll answer the last part of your question first. Have we been able to incorporate this complexity of interaction among species properly in our forecasts of what the future might look like? Generally speaking, no. And that's largely because being able to gather all the interaction data between species across the planet is pretty much impossible. So most forecasts have been based on very simple things like the thermal tolerance of a species, how hot a species can stand. I know, like, for example, people in Adelaide will be familiar with flying foxes dropping out of trees dead when it's 45 degrees for 3 or 4 days in a row. They're gray-headed flying foxes. They're not used to those kind of heat, those temperatures. It's usually the young ones that literally drop off the perch. And you can see them sort of piling up dead bats. It's not a pretty thing. So we every species has a thermal tolerance niche. So how cold they can stand and how hot they can stand. Now they can adapt to that. For example, if it's really, really hot, you can burrow in the ground and stay cool. A lot of Australian species do that. Or you can be nocturnal, just avoid the sun entirely, sleep during the day. Or you can seek water. You can have a cool bath. I mean, humans do the same thing. We seek air-conditioned rooms, and we jump in the pool when it's really hot, or we put on lots of clothes and turn on the heater when it's really warm. Animals have some adaptation, but not entirely able to do all of those things that we have because of technology. Nonetheless, there is a point when things die. And we generally say, okay, well, we can measure that pretty easily, the physiological maximum in a species. So it comes down to the specific physiology of the species. It's fairly predictable. We can pump that through a model and say, okay, these species are likely to exceed their thermal tolerances at this point in the future under this emission scenario, and that means this proportion of species will go extinct as a result. Now, that's just what we call direct extinction from climate change. That's the ones that succumb directly to the increased temperature. The second part of that, of course, is that, as we were discussing earlier, because of species dependent on those species that have gone extinct, ultimately their food or some other aspect that they require in their life cycle is also going to go the way of that original species, that one that succumbed to the direct extinction. And then those species ultimately go co-extinct. Now, a good example that a lot of Australians anyway might be aware of is we call these legacy trees in paddocks. You'll get huge gum trees, just remnants in big paddocks that have been paddocks for hundreds of years. And slowly over time, all the big trees around them have been removed. And eventually you get this sort of one tree in the middle of a huge paddock. And the nearest closest individual tree of the same species could be 20, 30, 50, 100 kilometers away. Well, trees obviously need to reproduce as well. They're living beings. They do that generally through pollination. Sometimes it's wind carried, sometimes it's insect carried. But the pollen needs to go to a male pollen needs to go to a female reproductive organ. Some trees have male and female parts on the same tree. Some split them up like we do in genders. It's highly variable. But anyway, let's just assume that it's a male and a female tree. Pollen comes out, it goes through the landscape, but if the nearest female is too far away, there's no pollination, and it dies. And so we have a lot of these things called living dead or zombie species, because they're still alive, but they're not reproducing, so they're not replacing themselves, and eventually they'll go extinct. And we see these legacy effects. Extinction debt is another term we use. So you're paying this debt from a past disturbance. It can sometimes be century scale. It really depends on the generation time of the species. For example, long-lived trees, it can be hundreds of years before you start to see that impact on the entire population. And that means that we have, again, this slow process of co-extinction that eventually will lead to an ultimate collapse that's quite precipitous.
Now, the concept of extinction is nothing new. It's something that's always been around. How to put this forward? There's obviously different contributing factors to the cause of an extinction, and therefore there would be varying rates of extinction. Right now, we're in the midst of a sixth mass extinction, which means there's been 5 before. Give us an overview of what contributes to an extinction. How does that sort of relate to the rate of an extinction? Does it happen over an immense amount of period of time, or is it quite sudden?
Okay, so yeah, we have to go have a little bit of a prehistory lesson to understand this properly. If we go back to the earliest evidence for life on Earth, 3.5, 4 billion years, it sort of varies depending on the evidence. There was a long period of very slow speciation, and of course extinction is happening during that time. Fast forward to today, and we've got this amazing abundance of different life on the planet. But approximately 99% plus of all species that have ever existed in the past, going back billions of years, are extinct. Now, that means that speciation, the process of evolution that changes species based on recombination and genetic drift and all the other things, natural selection that creates species, that means that process keeps slightly apace of extinction on average, otherwise there would be nothing left, right? So you think filling a pool, you've got a leak in the pool, that's your extinction. And if you got a tap filling it, that's your speciation. If speciation, the filling, isn't as fast as the leakage, then the pool level goes down and eventually there's no more water, right? So on average, that's what happens. But the thing is, in evolutionary terms, it's not a slow, gradual leak and a slow input of water from a tap. It's a great bloody earthquake comes up and then takes out half the pool water in one go, and then there's a slow filling again. So extinction isn't a gradual, it's always happening, but it tends to be interrupted by these mass events. And these are what we call the mass extinctions. What we call a mass extinction is a little bit arbitrary. It's these really big events that we see in the paleontological record. The general accepted definition is at least 75% of species going extinct within about 2.5 million years. 2.5 million years is a long time. Our species hasn't been around that long. So it sounds like something that's, it's a concept that we can't really get our heads around. But that's actually, geologically speaking, over the history of the Earth, that's a heartbeat. Now, have we lost 75% of our species today compared to, say, several hundred years ago? No, we haven't. But the rate at which we're losing species is as great, if not greater, than what we saw during those 2.5 million periods during mass extinctions in the past. Of course, there were hundreds of other smaller extinction events that didn't quite meet that 75% threshold. But basically what it's saying is that extinction is kind of chaotic through geological time. If we continue at the current observed and predicted rates of extinction that we see today, we will achieve 75% threshold. Again, it's an arbitrary threshold. It's big. We'll achieve that within centuries, not 2.5 million years. And that's entirely due to our endeavors, humanity, and how we've changed the planet.
And I'm just going to ask, because a lot of people associate ice ages with a high extinction rate, but talk to us about extinction rates in ice ages versus periods of warming like we're in now.
Yeah, that was sort of the common assumption through much of the last century, was that cold was bad, that great big icebergs and glaciated valleys and things like that would push species away and they would all go extinct. Turns out species, yes, they did move their distributions, but it was more likely the rapid warming events that precipitated these big extinctions, because it turns out that most species have a much better capacity to adapt to cold than they do to heat. There's a lot of physiological reasons for that, but also that the heating tends to come on much quicker than the cooling. It doesn't suddenly, it's not minus 40 tomorrow. It's a very gradual process where heating can actually happen even in the last, say, few 100,000 years. There's been heating events that have gone, 10, 12 degrees in less than a century. That's massive. That's the kind of huge transition that species really can't adapt to quick enough. Now, every species has the capacity to adapt in some way. As I mentioned, behaviorally, there's a physiological adaptation called physiological plasticity. And then there's evolved adaptation. You can adapt to new, if you have long enough, your genome has the requisite diversity to be able to sort of, through natural selection, choose genes that are more adapted to a new environment. But that generally takes quite a bit of time, quite a number of generations. Behaviorally, today I can say, oh, it's hot, I'll go inside. Tomorrow I say, okay, physiologically I might build up some capacity to sweat more. But then in the long term, I have to sort of change my genome so that I can handle, I don't die at 45 degrees, I might die at 50 instead. So the importance of warming now we understand to be probably some of the worst forms of climate-driven extinction throughout all time.
And how does that compare to other contributing factors such as land clearing, or varying land use, pollution, even concept of colonialism. If we go back just a few hundred years and introduce species and so on, where does climate change rank in terms of the factor?
Yeah, it's funny, there's been a lot of work recently about this whole concept of ranking, which is the worst. Humans love to rank things and put things in boxes, top 10, bottom 20, all these. It's kind of a distraction in extinction dynamics, because they're all bad and they kind of interact in very complex ways. So we don't tend to focus on what's the worst, what's the least worst. In the past, there is, however, no question that habitat clearance, so vegetation clearance, has been probably the main driver since the onset of the Industrial Revolution, really. That has driven more species to extinction than anything else, and will continue to drive things to extinction over the course of the next century or so. We've changed the surface of the planet dramatically. But that's in the past. So yes, there's still clearing going on, unfortunately. There's still habitat conversion, which is a nice way of saying destroying habitats. But if you look at the pace of land change versus the pace of climate change is overtaken habitat degradation as a principal driver. And it will for the foreseeable future, especially if we get these kind of cascade precipitous declines happening that our models are predicting now. It's not to say that habitat loss isn't a bad thing. It is, but it's probably shifted or will soon shift from being the dominant driver. Of course, as I said, there's a lot of interacting disturbance drivers like invasive species through, as you said, colonialism, and how pollution is affecting the dynamics of interactions of species, the accumulation of microplastics. We still don't have any real idea how that's changing the resilience of ecosystems. We think it's bad, it probably is, but it's very difficult to measure at that scale. So all of these things interact. And we did work many years ago talking about what we call extinction synergies. So let's say that you lose a certain number of species from habitat loss. And then a certain addition of species are lost from climate change. A certain number of species are lost from some sort of pollution effect. Well, if you just add those up, you say, well, okay, we're going to lose 20% from this and 10% from that and 5% from that. That would be 35%. But it doesn't work like that. They actually interact to make each other worse. So you can get that 35% actually is probably more like 75 because they make each other. It's like when you have a cold and then you get exposed to the flu. You're already immunosuppressed, or something has affected your physiology. You're tired, and that's why you get sick, because you're already compromised. It's a little bit like that interaction in a body's health. But this is at sort of the ecosystem scale.
And because you love the ranking, we're not going to talk about ranking, but Australia and New Zealand are regarded as some of the, I guess, let's call them hotspots in terms of biodiversity loss and so on. Just touch a little bit, perhaps more in your case, on Australia. How bad is it?
Yeah, well, Australia is in certain groups of species, we're doing very poorly, like mammals. I think we're still the world record in mammal extinctions. That's contemporary mammal extinctions going back, at least 5 decades or so. And we'll continue to lose them. But mammals are also the thing that we know the most about. So we tend to look at the big furry things first, and then birds are probably a close second. We tend to forget about reptiles and amphibians. Our reptiles are doing a little bit better, but our birds are doing poorly. New Zealand, of course, birds have probably been the worst hit through right up from the first human peopling, going back Maori to European invasion. And so it kind of depends on the area. New Zealand obviously has a very unique biota because of its island context and its isolation from Gondwana several hundred millions of years ago. So in a lot of ways, New Zealand has a special set of extinction circumstances and susceptibilities. Australia, being much larger, has the continental momentum to be able to withstand some of those smaller level perturbations. Nonetheless, both countries have been massively changed especially since European invasion. But that, of course, doesn't say that there wasn't any change before that. Humans change an environment, sometimes for the best, sometimes for the worst, as soon as they get there. It's really a process of the intensity of that change, and how many people are living on the landscape.
So let's dive into your paper a bit more. I know we've already kind of been talking about some of the takeaways from that, but you published this at the end of last year, and it's estimating the impact of co-extinctions on vertebrae from climate and land use change. Correct me if I'm wrong, I believe this is a continuation from some work you published with your co-author in 2018.
Yeah, that's right. So co-author Giovanni Strona, who Italian, obviously, a friend of mine, met him back in, when was it, 2017. He was at the European Commission research agency based in Ispra in northern Italy, not far from Milan. Lovely area. I happened to be in Italy for some other work, and we met up at his institute. He subsequently got a job at the University of Helsinki. He came and visited me here in Adelaide for a while, a little bit of an exchange. Giovanni is a specialist in network theory, and network theory is a mathematical way of linking units, and units in this case could be species, and that's kind of how we treat them. So a network theory provides the linkages between these units, which we call nodes. And it's a whole mathematical area. It's actually developed for physics and internet technology, really. That's how that kind of mathematical establishment happened. And we've adopted a lot of those processes and then, of course, changed them according to biological principles. So Giovanni and I, back in 2018, we put together work that looked at what we called extreme temperature change. So we're looking at like 10, 20, 30 degrees of cooling and or heating. And the main impetus for that was actually a very weird little paper that was published back in, I think, 2016 that said that, and a lot of your listeners might not be aware, but there are these wonderful little creatures called tardigrades, or water bears, and there's lots of different common names for them. And they're almost microscopic invertebrates with, they're not insects. Tardigrades, they live in almost every environment, and they're known for being, well, extremely cute. It's one of my favorite species. They don't even have mouths that we call mouths. They have these sort of weird kind of cylindrical, suction-y, rotating things, and they have claws on little fat pods that are for feet, and they kind of look like a cross between a bear, which you can get the water bear, that's where that comes from, a tick, and a velvet worm. They're just a weird, beautiful thing. But you can cook them, you can fry them, you can freeze them, you can shoot them into space, you can bury them under 300 meters underground. You can do whatever, and they still come back. They have this marvelous physiology that can adapt to almost any extreme. We call them extremophiles. They like extreme conditions. So this one paper came out and said basically, well, if the entire world turns to shit and everything dies, at least we'll still have tardigrades because they're these physiological superheroes. Well, as ecologists, we kind of scratched our heads and said, well, does that actually make sense? Because, of course, nothing lives in a vacuum. We all depend on other things. So we put together this work that tried to look at the extensiveness of those connections that included tardigrades, and looked at how tardigrades, how resilient they were in an ecosystem sense. So yes, they can tolerate themselves a lot of loss, but if their resources go extinct, it doesn't matter how tough they are, they're still going to go extinct themselves. So that was a really sort of a demonstration that all things are linked and that we underestimate our extinction rates if we only look at the individual species and their physiological limits. Fast forward a few years and we started this work to look at, okay, well, that was kind of a theoretical approach. We wanted to look at actually predicting the rates of loss that we are underestimating from current levels of predicted climate change to the end of the century. That was really putting into context of what we're seeing now and not just a theoretical, plus 10, minus 10 degrees, which would be catastrophic. But we're already getting into the area of 3, 4, perhaps even 5 degrees looking plausible by the end of the century. No, that's just insane. We've sort of abandoned 1.5. I know that's not a popular thing to say amongst the conservation community, but if we could keep it under 2, we'd be doing extremely well at this stage. If we hit 3 or 4, that's kind of getting into the catastrophic mass extinction stage. That's both in terms of what we've done before, in terms of the catastrophic extreme heating or cooling scenarios, as well as what we're seeing from our models now that link them to actual climate change. Now, a lot of people say, oh, you know, it's a model. You could be just as wrong as you could be right. Well, I think that demonstrates a certain misunderstanding of what models do. One of my favorite quotes is from a now dead biostatistician named George Box, who said, all models are wrong, but some are useful. You can't predict the future. So by definition, a model is a simplification of a complex system, right? You can't get every element in a complex system yet. So what you do is you try to get the major drivers of how systems change, the major agents within that system. And then what you do is you contrast scenarios. So we're talking about relative truths. I'm not saying that this is going to happen or that's going to happen, but if I pose two different scenarios to this system, this model, I can tell you which one is more likely. Another way to look at it is this one is least untrue versus that one, right? So it allows us to make decisions that are more informed. So we're not going to say that, you know, there's going to be this many species going extinct. We're just saying that if we make this decision or we cap temperature rise to this amount, that means that we're going to have, on average, a relative reduction in extinction by this magnitude. So that's how models work. Now, it's a model. It's wrong. Of course it's wrong. We have to make assumptions. We have to take data sets that aren't global in expanse. We have to make some forecasts about how things work. We have to take real data and sort of expand them to huge scales, and sometimes that's not feasible. But what we did do is we actually constructed what the world's biodiversity, that is the diversity of distinct vertebrate species, so these are, you know, animals with backbones, at a pixel level around the entire planet. So our pixels were 0.5 by 0.5 degrees latitude, longitude. So that's about 50 kilometers square, or 50 by 50 kilometers. And in each one of those little cells, we counted up the number of species that our model predicted based on these fundamental principles from all the different data sets we combined. And then we compared those to the actual maps that we have from the International Union for the Conservation of Nature, which measures the distribution of all species on the planet. And of course, not all species, but for the ones we have the most data for. And we compared those, our model, based on first principles, versus actual measured distributions, and they overlapped almost perfectly. So we know that we're pretty good at predicting where diversity is now. So by that extension, we thought we were pretty good at predicting where we're going to get the most losses and by what magnitude. Again, a relative truth kind of scenario. And so we're fairly confident that we're not too far off the mark. Whether it's 20% or 30% or 27.2, we don't know. There's a certain amount of uncertainty in these models, of course, but we can say that if we 2 to 3 degrees of warming, we're looking at potentially achieving 30 up to maybe 40, 50% loss within this kind of time frame. Now, that's another thing about this particular model, and maybe you were going to ask me this question, Emma or Ben, but it's not extinction per se. We were specifically modeling diversity loss. So the way I describe that is, look out your window today. Count up all the number of animal species that you see. Let's say you see 10 species. You see, a bird, a couple birds, maybe a bettong, koala, like there's koalas all over the place around here, that sort of thing. We're only looking at vertebrates, forget the invertebrates for the moment. And then in 50 years, you look out that same window at the same time of day, same season, and you count the number of species that you see. Chances are you're going to see about 20, 30% fewer species. That doesn't mean the species has gone extinct. It could be somewhere else. It just means that on average, in any given spot, you're going to get a reduction by this amount. Does that translate into extinctions? Ultimately, yes. But we have to take into account the entire range of a species, how many individuals in those populations there are, before we can start to talk about total extinction of a species. That is the loss of all individuals. That's actually our next step. We're sort of working towards that outcome. But for right now, we're really just talking about relative loss.
But I mean, given all of the interdependencies of the species, assessing the data at such a scale, that would have been hugely challenging. How powerful was this computer that you were working with?
Well, we used one of the EU's top supercomputers. That most academics have access to these computers through institutional arrangements. We do in Australia as well. Giovanni just had a really good access to the one that's based in Finland, funnily enough, considering he was in
Yeah.
Helsinki for a number of years.
Because you're making it sound easy, but like there's a lot of work that
Yeah,
goes into this.
and all credit to Giovanni. He did the lion's share of the work. It's multiple. When I say multiple, tens of billions of iterations of these models that look at any possible outcome or contingency, and we're trying to combine all of that uncertainty into an average response. And these models have a lot of complexity. So we're doing the individual species, but of course we have species that are spread in different communities all around the planet. And then within those communities, there are the top predators, and then the mid predators, and then the big herbivores, and then the small herbivores. We have plant effects, we have invertebrate effects. We also have migration effects. So one species can move to this other community over here. Now that can either result in a success in that it invades successfully, it finds a niche, it finds some food. It's outcompeted maybe by the indigenous species in that area, or it can become a food source itself and perpetuate a better resilience to that species. Species can also adapt to a certain amount of warming within their particular environments. Warming doesn't happen uniformly over the entire planet, so of course some communities are experiencing it much faster than others. We have also the component of trait diversity, so that's sort of links a little bit back to that idea of ecological function. So you have a number of traits: how big you are, how you breed, what your oxygen consumption may be, blah, blah, blah. All these different things that allow you to adapt to particular environments better or worse. So putting all that together means that there's a bucket load of computations that have to happen at each iteration. And we do this billions of times. And that's why you need these supercomputers to do it. Because you're essentially, well, again, it's a simplification because it's a model, but it's a virtual Earth of species. And we're trying to push buttons to see what would happen if we did X. That's how these things work. But yeah, I deliberately tried to steer away from the maths when we're talking about this sort of thing because it's just lost on people. And I mean, it gets me going, but it doesn't float everyone's boat.
Now, this modeling focus on vertebrates. How can we relate this to us as humans in terms of some of the sort of themes you would have got from the result? How does this? Because you've spoken about from a food web perspective, predators, pollinators, that kind of stuff. But us as humans, climate change has an impact on our food source, whether it's agriculture related or those that eat meat and so on. How can we relate or translate some of the outcomes of this model to us as humans? And again, if we stay within the 1.5 or 2 degree, if it goes to 3 or 4 degrees above, how does that impact us?
So yeah, modeling non-human species is sometimes a lot easier because we have a very defined set of capabilities and limitations within a species. Humans are quite different in the sense that we have technology that allows us to buffer ourselves from extremes. For example, we go in the house and turn on the aircon, or in the car when we're driving to work, or we put on clothes when it's too cold, or we can seek medical attention, interventions that aren't otherwise available to most species. Food supply. A lot of us live in places that don't grow enough food to support our populations, but we bring it in from elsewhere. Transport is a huge component of the large human population that we have now. Items are made here, they're used here. Transport is a huge component. That's basically our economy right there, is allowing people to live in places that they wouldn't otherwise be able to live in because we can just shift resources around. We can also increase the productivity of an otherwise passive environment through things like agriculture. We've been doing that for 12,000 years. more or less, that we can suck nutrients out of the ground and turn them into cows that then people eat, or crops, or, that's our food source. But 80% of our food crops, on average, globally, require some form of animal pollination. Half of that comes from bees. One species of bee, the Apis mellifera, the European honeybee. So let's say that European honeybees disappear. We're screwed. We really are, because 1 in 6 mouthfuls of food on average globally comes from one species. Now that blows my noodle. Not only is that the case, but of course the human population is still growing, and it will for the foreseeable future. There is a slight potential of peaking near the end of the century, depending on certain scenarios. We do scenario modeling for humans just like we do for climate. We'll still have to, at current projections, we're still going to have to double our caloric or energetic production of food by 2050 just to maintain where we are now. And of course, not everyone gets all the food they need. That's a distributional issue. Up to 1 billion people on the planet suffer from some form of malnutrition or nutrient-related immunosuppression or some other thing. So we're still not getting enough. So just to stay where we are today, with 1/8 of the world's population suffering from some form of nutrient deficiency, shall we say, not outright hunger necessarily, but nutrient deficiency. Just to maintain where we are, we're going to have to double our production. Meanwhile, we're losing all these species that do stuff for free. If we had to go out and pollinate everything by hand, we couldn't do it. So, plus then, of course, you get the effects of direct environmental extremes affecting our yields. For example, for every 1 degree of warming, we lose about 6% of our wheat production. So humans going up, species that pollinate and do other things for us going down. We're also increasing the proportion of our individuals within middle classes. That means eating more meat, unfortunately. That means a higher consumption rate in its own right. So everything's going in the wrong direction. So hunger of food, and of course water is very closely tied to that. Those kind of conflicts that will arise and are already happening will continue to present a lot of political issues and warfare, or at least conflicts will result as because of that. We see that in lots of places that are already sort of politically unstable, and it will get worse. Now, we're getting into sort of really uncharted waters here, because it's difficult to predict all of these very unpredictable components in a complex system. We are part of a complex system that's embedded within the biosphere, which itself is a complex adaptive system. But one of those corollaries, of course, is if you get localized collapses of food production, you're going to get refugees. Some back-of-the-envelope suggestions show that we could be having, all other things being equal, ignoring climate change, current political instability, that we could be sort of in between 80 and 120 million refugees coming out of Africa every year by the end of the century. Most people think, refugees, they end up going to wealthy countries. 80% of all refugees today end up in other low-income countries. They take on the bulk. So these are the countries the least capable of taking on this extra burden. So this is where you get people fleeing borders, refugee camps, famine, warfare. And so the spin-off of this is more and more resources that are sequestered by fewer and fewer individuals, leading to more and more conflict, and ultimately more people suffering than they are today. And that's a cascading effect of environmental resource loss, and we're seeing that happening now. If you go back to sort of probably most of the major political upheavals, mass refugee migrations over the last 50 or so years, most of them have an environmental trigger. We can say, it was this leader that made that decision that pissed off those people that's led to that conflict. But if you look back, it ultimately comes down to a resource penury. And environment sets the stage for us to get aggro with each other. And when you're hungry, when you're thirsty, you don't really care about the welfare of your neighbor. You just want to sate that interest. We're very basic in that sense, and all species are, and that's completely understandable based on our biology. But we transform that into a political relationship and a political outcome. So I always say to people, look, the future is not going to be as nice as it is today. How not nice it is somewhat open for debate, and this is what we're trying to do by putting together these models. But we're not going to prevent a lot of suffering. What we can do, though, is that we can make it less worse. we can like I always say to my students, the future is going to be shittier. It's just how shitty it's going to be depends on us and the decisions we make. That kind of gets me out of the bed in the morning. If when I was a bright-eyed, bushy-tailed undergraduate and I thought I could save the world, that was a good incentive to do what I was doing. But then when I realized that I'm not going to save the world and it's only getting worse, everything we're measuring is getting worse. So why do I bother? When I made the transition to I can't save the planet, but I can make it less shitty, maybe, that keeps me going. And there's been a real psychological shift in people in my discipline, at least, towards that goal. And a lot of people say, well, that's very pessimistic. And I think that's more optimistic pessimism, in that you can have a role. It doesn't mean that you're going to prevent disaster. It just means that disaster won't affect as many people as badly as it could otherwise be. And that's actually is quite calming and fulfilling as a scientist, if we can do that. Again, it's a big if, because I don't make the political decisions. Yes, I vote. Yes, I spend my money in particular ways, and that's one way of exercising my democracy. And more people are doing that, and that's great. But if ultimately society ignores these warnings, then they're going to suffer more as a result. So we're just really trying to get people to say, look, we don't know the future, but we can make more informed decisions about the probability of certain events arising.
Yeah, and if you're grounded in reality, then you're more likely to be able to do the work to actually get the outcomes that are needed, rather than walk around with rose-colored glasses on thinking everything's fine. But this kind of brings us to the timing of your paper. It came out just before the UN Diversity Conference. Any thoughts on the outcome from that conference? Are you pleased with the takeaways there?
We didn't plan it that way, but it was actually, I think there were 3 or 4 days left in the COP when our paper came out. So it wasn't right before, it was actually during and near the end. We had a few people present some of the work. I know that Tanya Plibersek, our environment minister, was there, and she was given a briefing about the work, and that it was noticed by a few people. It was actually, the paper was just written up in a journal Nature Climate Change, which is a very big Nature publication, just yesterday. So it's getting some notice, and that's great. I hope that it gets worked into the next IPBES report, the Biodiversity Assessment Report, for the next iteration. I'm not sure when that's going to happen, as a demonstration of the linkages to what the IPCC is doing versus what the biodiversity mob is doing. And it was recently, only a couple of years ago now, I think, acknowledged officially that the linkage between solving climate change and solving biodiversity crisis is so close that we can't really do one without the other. And I think this is just another piece of that puzzle that demonstrates that relationship. And how comes so? If we lose societal capacity to behave and responsibly and make long-term decisions in the appropriate way, in other words, if we have enough food, we can make lots of good decisions about mitigating climate change. But if we're just trying to scrabble around for something to eat, fixing the future is the last thing that we're going to think about. So these are how these things are all interrelated. For example, let's say, I don't know, if I don't sleep well the previous night and I don't have to go to work the next day, chances are I'm not going to be bothered to go have a shave because it takes effort, like today. So when you have capacity, when you're in a good physiological health state, you have the flexibility to make a lot of decisions about your life. When you're really just thinking about, oh, my tummy hurts, or I feel sick, or I'm depressed, you kind of let all those other things go because that's not your immediate concern. And that's scale it up to entire societies. As our biosphere collapses and it starts to affect our standards of living, we're going to be less and less concerned, ironically, about the future because we're more concerned about the immediate alleviation of our suffering. And that's what really concerns me. And we wrote a paper a couple of years ago about that. The fact that all these challenges are presenting themselves, we know that they're bad. We can make some reasonable predictions of where we're going. And yet our political capacity seems to be going the other way. We have less and less political will to make big decisions because of all sorts of interrelated things, the way our economy is structured, the way that we still have corporate capture in our governments, that there isn't a true democracy anywhere on the planet. There's always some form of corporate or financial capture. We don't make decisions that are for the greater good. We make decisions that are based on the acquisition of wealth, generally by a small proportion of society. Until we fix some of those things, we're not going to be able to make big, uncomfortable decisions that have to be made. And I fear that crises will have to be experienced before we start to think, maybe we should do something. And then it might even be half-baked by then. So again, this is why I'm an optimistic pessimist, because it will be bad. It's just how bad it will be, I'm not entirely sure. That's a political decision.
So if I want to go see a spotted quoll, or if I want to go see a pygmy possum, do it now?
Yeah. I have a photo I took I was in the Kruger National Park in South Africa back in 2016, I think. Took my daughter. I had a conference there. It was wonderful. And I took this photo of a white rhino in the park that was it was dusk and it was kind of running away from me. And the exposure on the camera made it look kind of like the rhino was a phantom, sort of fading out. And I called it ghost rhino because as I was in the park, at that very moment, on average, 2 rhinos were being poached per day. In the biggest, most well-protected, best-financed national park in all of Africa, and they were still losing that many rhinos a day. And I just said, look, if you haven't been to Africa and haven't seen a rhino, go now, because the likelihood of seeing them in 20 years is pretty slim. Again, I don't want to put a time on that, but yes, if you have an opportunity to see something now, see it, because there is a decent chance you won't be able to later.
So as individuals, and following your mantra of making this planet a little bit less shit, which we actually have on record in a previous episode from you.
I couldn't remember if I'd said that before.
It's good to be reminded. What can we, we've spoken about political systems and it's the same arguments you now get in conversations about the whole concept around degrowth, who should be leading the charge, corporations, leadership, in terms of politics, or us as individuals. But let's just focus on us as individuals. Let's get ourselves out of this big pit that we've dug ourselves. And what, as a takeaway from this, it's important to understand what is happening, what could happen if we keep carrying on with this trajectory that we're on. What can we as individuals do to make that small impact?
Yeah, I have my canned set of answers for that, but I'm going to expand on that a little bit here, because I'm sure I've said some of these things before. But before I do, I had a sort of a little discussion on social media the other day with one of my colleagues who was talking about environmental funding and how that there's a lack of environmental funding. And we basically came to the conclusion that there's no lack of funding. It's a choice to fund specific things. Like, the national or the state budget comes down once a year. Certain proportion is allocated to health and then education and this and that. Some people win and some people lose. Almost universally, environment is in the less than 1% of that. And that's everything, right? And we have special initiatives, the koalas are going extinct. We should invest 10 million, and that's what we've done in koalas. Now, thankfully, the corollary of that is that we're probably going to save a lot of forest, which saves a lot of other species potentially that live in those forests. But we do this sort of very piecemeal, one at a time kind of, that's reactive.
It's
reactive. we don't have a proactive approach, and proactive approaches require long-term vision and funding. So in pressuring our representatives, that we always whinge about not enough funding for schools and health, but that actually takes up over 80% of every budget. Those two items alone. If we even doubled to 2% or more, 3% of what we're spending on environment, and that's everything from restoration through to protection, through to offsetting, all sorts of components that deal with that. Feral animal removal, reintroductions, plantations, you name it. If we could put a little bit more emphasis on that, and I'm not talking about we'd have to sort of dump all hospital funding, because that wouldn't be politically palatable. But if we can pressure people to say, look, our environment it's not about a lack of funding, it's about a choice. And if we choose to put more time and funding and effort into these components, we have a chance of building some resilience into our systems. Now that's just on the very almost direct things that one can do in terms of how we address extinction directly. But there's a lot of, and I think this is where I'm getting into territory that I might have covered before, a lot of things that we can do through voting, through representation. In this country anyway, we've been talking for ages about integrity commissions that have some teeth. So taking politicians to task about corruption, to just dodgy behavior. And in a lot of ways, we do have a very corrupt system, but because it's legal, it's not counted as corruption on the International Corruption Perception Index. But it's a form of corruption, and that's essentially when political donations drive the decision making. And every democracy in the world has that, some more than others. So by definition, as I said earlier, there isn't a democracy anywhere on the planet. It's all one form of a plutocracy, some more than others. In other words, you buy the decisions, and that might not be direct. You don't say, okay, if I give you $10,000 in a bag, that you're going to do this policy that helps me as my industry. But that's essentially what happens. So can we at least put more emphasis on integrity commissions and then move towards massive reductions in political donations and have more of a public funding system? These are all possible. These models and frameworks have been developed by political scientists for years. We know how to do this. Again, it's a political decision. Other things, of course, that directly relevant to your audience in particular, yeah, I mean, vegetarianism is one of the biggest things an individual can choose to do in terms of reducing your impact. It doesn't mean that you make it disappear, but there's an old joke, it's the woman holding the placard that says "Save the planet, kill yourself," because ultimately that's the only way that you really remove your footprint. Everyone has a footprint, but you can drastically reduce that footprint, and of course all of the other things, including flying overseas. I was a big hypocrite pre-COVID about that in particular. COVID really sort of taught me, I don't have to travel that much, and B, I shouldn't. So that's really changed how I view things. But even other things that people don't immediately equate with environmental custodianship, and that's the choice to have fewer children. There's no magic number. Well, there is in sort of a large scale effect, but if people made the decision that they were going to have one fewer children than they would have otherwise had, that's one of the biggest impacts an individual can make on their legacy, a lifetime impact on the planet, because of course it goes beyond their own generation. That's their legacy. Now we have the luxury of being able to do that because we have such high infant survival in wealthy nations like ours, that we can do that, and we're pretty much guaranteed that those children are going to survive. I have a paper actually coming out in 2 weeks that looking at the relationship between child mortality and human fertility across low and middle income nations all across the planet. And it turns out the number one determinant of human fertility is child mortality. So if we get a handle on increasing child mortality, fertility will drop, and therefore our population rate of changes will go down as a result. And that will put much less pressure on the planet. Funnily enough, contraception does contribute, but it's very much a minor effect. It's actually more about mortality, which of course links into the Sustainable Development Goals of the United Nations, reducing child mortality, increasing the prospects of young women in particular, education, the ability to choose one's reproductive life, and being able to pace birth events and not be sort of under the yoke of maternity for the duration of their entire adult life. These are things that free people up to have a better life as well. So there's a lot of corollary benefits, of course. Getting into dicey areas, we looked at religion too, because there's a common assumption, at least at that scale, that religious adherence increases fertility, which turns out not so much. So again, at this scale. So there's a lot of little things like that seem little, but actually can have huge impacts down the track.
And equality of healthcare as well.
Well, yeah, healthcare is a key to all that, because again, think about coming back to that very concept of child mortality. If your children are guaranteed pretty much to survive, there's no need to have 15 or more kids like we used to, right? There's cultural elements in that. There's religious components to that. There's human rights. It's a very complex situation. Every time I write about human demography, I get death threats. It's inevitable. That just goes into the hate mail folder. It's a growing folder. But if the message gets to broad enough community, of course these have to be ethical, and they have to be non-coercive, and they have to be culturally aware and sensitive. There's no one-size-fits-all approach to any family planning or any other sort of thing that deals with human demography. But there are good ways to do it, and health is wrapped up into all of that. So yeah, that's a very good point.
I think we're going to wrap it up there. I think there's a lot to let sink in. There's a lot to think about. But Corey, thank you. On behalf of all of us, our listeners, and everyone else that's going to listen to this episode, you're just like so many phenomenal scientists. Communication, we've said this so many times, but the way, there's so many brilliant minds, so much brilliant work, but how it's communicated in a way that we can understand and actually do something with that's something you're brilliant at. And so that's, it's important to thank you for that, because we need more of that. So these are the kind of conversations we certainly look forward to. And, it's the mathematics behind this, the modeling, it's a lot to take in, but.
Well, that's a very kind thing to say, but I'll turn that around too and say that the opportunity that your venue and what you provide to do that is an essential part of that process. Most of the time it's sound bites. I'll get, 10 seconds on ABC News, between 6 and 6:10, and that's it. That's what people hear. This is an opportunity to dig into it and to discuss the complexity and the subtleties, and then link these sometimes esoteric things like extinction to our own well-being and our standard of living. And that's the disconnect I think a lot of people have, is that why should I give a shit about a species of centipede going extinct in some rainforest somewhere that I'll never see? If we dig into that and have the opportunity to expose those relationships, people go, okay, well, I can't see the direct relationship, but I can see how, the loss might make my life just a little bit more shitty. And I don't want that. And that's once that penny drops, and it could be a very, very light penny, you're still going to make a move in the right direction. And that's, I guess, so I'm very thankful for this opportunity.
Well, it's only a pleasure, and maybe we'll look at giving you a 3-hour slot. But we certainly will have you back on the show again, that's for sure. You never stop publishing. There's always going to be something that piques our interest again. So, firstly, again, thank you so much for your time, the amazing work that you do. And, here's to our listeners, to all of us, making a little bit of a contribution to making this planet a little bit less shitty, quote unquote. Professor Corey Bradshaw, thank you so much.
Mic drop.
Thank you. I think that's going to go on my headstone.
Thank you for listening to the Lentil Intervention podcast. If you found this interesting, make sure you subscribe and share it with your friends.